a 3D iris scanner from a single image using convolutional neural networks. Greetings, my name is Daniel Benalcazar, and this is a joint research between Universidad de Chile and the University of Notre Dame. The motivation. Traditionally in iris recognition, a 2D image of the iris is used for the analysis. However, the iris is not a flat structure. It has two muscular systems and a sphincter, which allow pupil dilation to control the amount of light that hits the retina. The muscular fibers produce a relief in the surface of the iris, similar to a landscape with peaks and valleys. This is exactly what we aim to capture in this research. Depth information will provide an additional degree of freedom in iris recognition. This could increase iris recognition performance even when only a portion of the iris is available for the analysis. The methodology. Sheng et al. Proposed T-squared-net, a novel architecture which allows training with real and synthetic datasets to overcome the scarcity of real data. The network is divided in translation and task. In this work, the translation part performs domain adaptation on synthetic iris images to make them look more photorealistic. The task network produces depth prediction from real and realistic iris images. Sheng et al. Also described several training schemes, such as vanilla and full. In the vanilla approach, translation is trained first, and then, over the results of the translation network, the task network is trained. On the other hand, the full approach consists of training translation and task simultaneously. In this work, we use both the vanilla and full approaches to train several state-of-the-art networks. We also introduce iris depth, a network which combines the GAN of T-squared-net with the depth prediction architecture of dense depth to increase performance. For the real iris dataset, we acquired 26,000 images from 120 subjects in several dilation levels. Both eyes were illuminated using lateral and frontal visible light. For the synthetic iris dataset, we rendered 72,000 images from 100 virtual irises simulating the same illumination conditions of the real irises. We added eyelids, eyelashes, and reflections in order for the networks to learn how to segment those features. The results. These are the 3D models produced by iris depth. The network learned to predict the depth of every pixel in the image from visual cues, such as shadows produced by iris features. Since eyelids, eyelashes, and the pupil are segmented in the 3D models, they can easily be omitted from the analysis. At a resolution of 256 by 256, the 3D models have 65,000 3D points, which is 6 times larger than current structure-from-motion-based methods. The density of those 3D points is always constant, regardless of iris texture. Producing an iris model from a single image has additional advantages over structure-from-motion. There is a reduction in acquisition time, processing time, and storage. Moreover, there is a complexity reduction in the system since multiple images from different perspectives are not needed. The 3D representation of the iris has also potential applications in ophthalmology, as a slice of the 3D model can be compared with an optic coherence tomography (OCT). We compared 8 OCT slices of a subject with the 3D models produced by all the trained networks. The model produced by iris depth is very similar to the OCTs, and it produced the least amount of error. We also produced a 3D rubber sheet model as a proof of concept. The 3D rubber sheet has the same information as a 2D rubber sheet in the XY plane. However, there is additional information in the Z-axis to be exploited. Finally, we performed preliminary iris recognition tests. The proposed 3D rubber sheet produced genuine and impostor distributions with more separation than those produced by the traditional 2D iris code. This illustrates the potential of 3D iris scanning in biometrics. Thank you.